We'll be looking at the shortest path problem and then applying the shortest path procedure to determine what is the best route on a road network. Before doing that, we're going to start with a small example that illustrates a relatively new feature in Matlab, the ability to create graph objects. In Matlab, the graph object, if we do help on graph, we get information about what this creates, and what it does is it starts with an adjacency matrix like we were using previously to create graphs and networks in our previous discussion, and it uses it by applying that as a single input argument to the graph object. It then creates a graph object G, and that graph object G then has a series of properties. One is the set of edges and nodes that comprise the graph, and then a series of methods which are essentially functions that the graph can be applied to. And the types of functions include things like shortest path, breadth first, depth first search through the graph, max flow, minimum spanning tree, and so on. And also you can plot the graph. So those are nice capabilities. It says see also digraph. If you do help on digraph, you can see a similar type function. The main difference between a digraph and a graph is a graph or network that has only undirected edges, and that a digraph has directed edges. Previously, when we discussed graphs and networks, we mixed both together and just distinguished whether or not a particular edge was either directed or not directed. And we did that by looking at the arc list matrix. And if we wanted it to be undirected, then we put a minus sign for the J column of the IJC or IJD arc list representation. Matlab, using the graph and digraph procedure to create these two objects, that's all done as part of the object. There are advantages and disadvantages to using the object. The advantage of the object is that it gives you more capabilities in terms of being able to do a lot of different methods and provides a lot of different additional functionality. Probably the only disadvantage is from a speed point of view, it might be slightly slower. In terms of the script, the cell for this example shows first the creation of a random graph, and I think this is interesting to look at in terms of how, if you wanted to create a random graph, how you can do that pretty easily in Matlab. Essentially, we just want to create the adjacency matrix corresponding to the random graph. So I'm going to set the random number seed to a value so you can see this, and then I'm going to call the upper triangular function in Matlab, and it'll create a matrix, a 20 by 20 matrix of random values between 0 and 1. And then the 1 means I want to take the starting the row just above the main diagonal. So the main diagonal will be 0, and then everything above that will have values between 0 and 1. Then I'm going to call the spy command to display that result. So when I do that, this is the, so all these dots represent non-zero values. And then what I'd like to do is make it a symmetric matrix so that it represents undirected edges that have the same weights in both the ij and ji directions. So to do that, I can take the transpose of W, add it to the original W, and my then resulting matrix W will be what I'm looking for. So when I do that, I'm going to do spy again together with SHG, so I bring the figure to the foreground. So now I have the desired representation, but now I essentially have a complete matrix where I have connections between all of the nodes, and I'd like to make it a more sparse matrix. And I can do that by making any of the edge values that are less than 0.8, setting those equal to 0, and then setting all the remaining ones equal to 1. And when I do that, I end up with a sparse set of edges in my matrix. And the key thing is here that these are all symmetric. So the structure is the same along the diagonal. I'm going to use that adjacency matrix W then to create my graph object. And if you look over here in the workspace, you can see that G is a graph object as opposed to just a double matrix like the adjacency. Then we can call the plot object, and that brings this to the foreground. And you can see that without having to specify the coordinates of where to plot the nodes, Matlab has done its best to actually create a reasonable representation of the graph. Again, this was entirely a random graph. So what it's done is it's decided to locate different nodes at positions to try to minimize the number of edges that cross each other. So this, in some sense, is a heuristic that's used to display the node in the best possible means without having any excessive amount of overlap. So this is one of the nice features of having a graph object, in that, if you don't want to have to manually yourself determine what are the coordinates for all the nodes, then by just plotting that graph object, it'll do its best to actually give you a reasonable display of these points. This is probably the one best feature of using the graph object. Even if otherwise you don't really need any of the other features, just this ability to easily display the object is very helpful. Then also the edge property of a graph object, I'm going to take those edges and assign it to t. And if we look at what t is, it's actually a table. So it's creating a table object, and it tells us the end nodes. So really this is equivalent to our arc list representation, where we have the I, the begin or I value, the j or n value for each of the edges, along with the weights. Again, these are for a graph, which these are all undirected, so there's no negative sign needed because it's for a graph object. So by default, they're all undirected. Then we can create our convert our table into a matrix by taking just the end nodes, which are the ij values, together with the weights, and we can assign that to an ijg arc list representation. And then with this, you can see that we essentially get almost the same thing, the difference being that here we don't have the negative sign, whereas when we do it in this order, we have the negative sign. Also, the ordering is different. Our first value here is 3 minus 4, and here the first value starts with 1. So these are ordered in terms of increasing I value, whereas the adjacency to arc list representation is not done in that order. If we sorted it, we would see that they are the same representation. So again, these are just two different ways of doing the same thing. For the class, we're not going to be using the graph object for any significant procedures, but it's, I think, important to realize that it does exist, and one of the main features that is very beneficial is that ability to plot objects. The reason we're not using the plot for most of our applications is that the nodes themselves are located at longitude and latitudes. In most logistics engineering applications, the location of the node is very relevant to the problem. But if you're using graphs to represent some non-geographic set of nodes, then this ability to have them automatically determined can be very helpful. Next, we're going to be showing how to actually solve the shortest path example that was talked about in class using the Dijkstra procedure. So first I'm going to create the arc list representation corresponding to the graph that's given on that slide. And then first I want to show that it can be solved just as a linear program and solving it via the min-cost network flow procedure. And then after that, I'll solve it using the Dijkstra procedure. So if we didn't know that this was actually a shortest path problem that we can solve using Dijkstra, if we think about it more generally, we can view it as a min-cost network flow problem. And in this case, there's a total of 6 nodes. So if you set the node 1 to have a flow into it of 1, and then to have node 6 have a demand of -1, then the other 4 nodes are transshipment nodes with 0. So S represents the net node supply. So we can define that. So that, together with the arc list, can be used to generate the parameters needed for the LP representation. So if you look over here, LP is a 1x7 cell array, and those are all the 7 input arguments needed to solve as a linear program. We can take those and then solve it using Matlab's built-in LP solver. We get this as an answer. It has a total cost of 13, which if you look at the slide, when we did the Dijkstra procedure manually, You can see that that is the shortest path distance. And then we can convert it into a min-cost network flow representation by using the LP2 min-cost network flow. And when we do that, we get this as the solution. So again, this is similar to the min-cost network flow types of conversions that we talked about earlier. So essentially the shortest path problem can be viewed as a min-cost network flow problem. Next, we're going to then use the Dijkstra procedure to solve the problem directly. So a question then is, why go through the trouble of showing that it can be done this way if we have a specialized procedure? Well, I think the reason is that if you want to have the shortest path problem have additional considerations like bounds on the arcs or nodes that are capable when you model it as a min-cost network flow, then those capabilities can be included when you solve it this way. If you solve it just using the Dijkstra procedure, you don't have the ability to do that. So when you have additional considerations, it can be helpful to actually be able to solve it as a min-cost network flow, or more generally as a linear program. So it's not really a waste of time to be aware of this as an additional modeling capability. But if you do know it's just a standard type of shortest path, then you can directly solve it as a shortest path problem using Dijkstra procedure, as long as you don't have any negative arc links. If you have negative arc links, then you need to use other types of shortest path procedures that we're not going to be covering in this class. The reason being that they typically don't arise in a lot of logistics engineering applications outside of project scheduling, which is not something that we're going to be covering in this class. So again, it's not something that is going to be considered. So in terms of solving it, there is a procedure called DIJK in Matlab that gives the Dijkstra procedure, but there's another one called Dijkstra demo. And the only difference between the two, they both give you answers to the shortest path problem, but the Dijkstra demo procedure implements the code that matches the pseudocode given in the slides for the shortest path procedure. If you solve it using just the Dijkstra procedure, the code itself is more complex because it includes some additional features that help speed up its operation, but don't make it any easier to understand. So the demo procedure is a more straightforward procedure. Additionally, the demo procedure also shows the intermediate steps in the solution of the procedure. So when we use it to solve this, what it displays are all the different labeling steps. So in this example, each star represents which is the node that's labeled at each step of the procedure, and then what is the current distance estimate for each of the nodes, and then additionally, what are the predecessor values. So initially, everything starts off with distance of infinity except for the initial node. All of the predecessors are 0, and then as you go through the steps of the procedure, you end up with the final result that has a total distance of 13, and then the resulting sequence of nodes from origin to destination is defined as the sequence P. So starting at 1, you go to node 3, 2, 4, 5, and then ending up at 6. All of that is recovered using the predecessor values. So this last set of predecessor values can be used to actually generate this path sequence. So for example, we ended up at 6, which was our destination. It said the predecessor of 6 was 5. So in terms of the path, from 6, the preceding node was 5. And then looking at 5, its predecessor was 4. Looking at 4, its predecessor was 2. Looking at 2, which is over here, its predecessor was 3. And then 3's predecessor was 1. And then when we get to 1, its predecessor is 0, and that's when we know to stop. So to recover the path, you start at the end, then go backwards through using the predecessor values, and from that you can then create the entire path. So you'll see later that we'll be using this predecessor information to recover the path. The reason that it's important to have the predecessor information in addition to the path information is that from the predecessor information you can determine the shortest path from any of the 6 nodes back to the original node 1. So essentially you have 6 or actually 5 different paths that can all be generated from the single vector. Whereas if we listed the paths, we'd have to list 5 separate paths. So we get an economy by specifying just the predecessor as opposed to the all of the individual actual paths. And then there is a function called pred2 path that allows you, given the predecessor information, to generate the actual path. So you can recover that. So what the demo procedure does is, as a last step, it calls pred to path to take this predecessor vector and convert it into the actual path. In terms of complexity, in class we talked about the different types of complexity for solving the shortest path problem. So in our example, n, the number of nodes, is equal to 6. And in terms of solving it, the different options that are available, if we do the standard Dijkstra procedure, like in the Dijkstra demo code, that code is essentially an n square. So given the number of nodes, the complexity of solving it is proportional to n squared. There are more efficient procedures that use Fibonacci heaps, and the step that requires the Fibonacci heap is to select what is the minimum current unlabeled node to be included next in the procedure. And that one step naively is n. You basically have to look at all of the nodes, so it requires n complexity. By using a Fibonacci heap, you can reduce n to log n, and for large values of n, that's a big difference. In this example, for n equals 6, it's only 36 versus a 10.75. And then if we solve it using a LP, or min cost network flow, then as a, the best case scenario for solving a linear program is n to the 4th power. So for this example, that would be 1,296. So in terms of efficiency, either of the Dijkstra procedures are a lot more efficient than the LP procedure. So luckily, computers are fast enough now that we can not have to worry for some problems about using the LP. But for linear programming problems, they're really only, for shortest path implementations using linear programming, they're really only something you want to do when you want to add additional features. Very quickly, these problems can explode for realistic size problems. So the next example is more realistic. It has a total of 70,000 nodes, and that's the approximate number of road nodes in the United States that trucks can travel on. So it doesn't include all the residential streets. So for that more realistic size road network, if we run the same examples, if we use the Fibonacci, we have under 1 million. So that's actually fairly fast. That's what Google Maps would be using. If you use the Dijkstra procedure, it uses a Fibonacci heap-based procedure that is actually the same method that's available in the graph object. It used to be that that was only available in the bioinformatics toolbox in Matlab. So I've been using it as part of Matlab for quite a while because of its efficient implementation. It's not possible to implement a Fibonacci heap efficiently just using Matlab itself. Basically, there are not the procedures to do that efficiently. So you need to use some toolbox like the bioinformatics toolbox that actually implements it in C++, so it can do the Fibonacci heap efficiently enough that you realize the speed benefits. The code implemented using just the Matlab procedure of Dijkstra, the best you could do is just under 5 million. So that's a big difference. Actually, excuse me, that's 5 billion with a B versus this is under 1 million. So here you have a big difference. So if you want to use the naive or n squared Dijkstra procedure, that's going to be quite time consuming. And then if you solve as a linear program, I'm not even sure how large this number is, but it's way bigger than you'd ever want to consider solving. So again, for any kind of realistic type of routing procedure, you do need to have that Fibonacci capability. That's available in Matlab, but it's not something that you can write the code directly. You have to use the built-in procedure that's in the bioinformatics toolbox, and now it's actually one of the shortest path procedures that's within the graph object that we talked about earlier. Next example is a network that I'm going to create, just a sort of a notional road network connecting different cities that are within 100 miles of Raleigh. Again, this is just a way of generating a random, somewhat realistic, sort of a pseudo-realistic road network. And I think this is useful to kind of see how you can do this, because one of the difficulties in a lot of applications are generating data, and it's convenient in Matlab in many cases to be able to fairly easily generate random data that you can then use to test different types of procedures that you're working on. So first I'm going to determine where Raleigh is. And I get the longitude, latitude of Raleigh, and then I'm going to determine all of the cities that are within 100 miles and then have a population greater than 30,000. So when I do that and then plot, I end up with these set of points. These are all the cities that are around Raleigh. And then to get the road network, without actually getting the actual road network yet, I'm going to use the Delaney triangulation as a reasonable approximation of what the road network could be. So calling that. And then I'm going to take the triangle information, which if you look at it is a 24 by 3. So it gives the coordinates of all of the vertices in the triangulation. There's a function in Matlab that converts that set of triangle vertices into an arc list representation. And since there's no weight associated with it, I'm just going to assign it capital IJ. And then to assign the weights to it, I'm going to determine the great circle distance for all of the edges using the distance function. And then I'm taking an entire matrix, and then since the values I want sorted by the IJ values, so the first input argument here are the I values, which is the first column of the IJ arc list representation. The second input argument is the second column, so that's where the 2 is, and that corresponds to the J element. So those give me the I's and J's that I'm interested in, and then applying that to the distance matrix, that sorts the distance matrix in terms of rows and columns so that all of the IJs I'm interested in are located along the diagonal, and then I can call the diagonal function to have them sent to just a vector D that represents those distances. Again, that's a basic technique that's in the basic concepts for Matlab of converting IJ indices into the actual values along a vector. And then I'm going to bump it up by 20% to account for security. I'm going to round them so they display as integers. And then now I'm going to add it to my arc list 3-column matrix. Then I can display them using pplot. So these are the actual roads. And then the last thing I'm going to do is display the actual distances in miles between all of us. So this is use the ability of the pplot command to actually display strings along each edge, and those strings are the distances converted into a cell string. So I take the numerical value of the distance and convert it into a cell string. This is part of Matlab, num to cell string. So it does that point. And then the last thing I might want to do for this plot is to number the actual nodes. And there are 2 ways to do that. One is to just number in parentheses next to each node. And then a second is to do the number inside the node. So if I wanted to plot numbers in parentheses next to each node, I could do this, which is in this comment here, but I don't want to do that. Instead, I want to, since there's a small number of nodes, I want to have the number inside of each node. In that case, there's a method or an argument, a way of using pplot such that if we say num node, and then we can specify the edge color, which in this case is going to be black. And if we do that, then what pplot does is specify each node as a number. But then they're not actually numbers. These also really correspond to names of cities. So the last way of labeling the nodes is to specify this with the name of the city. It's kind of hard to see. There's a lot of overlap here. So if I blow this up a little bit, you can see now that now you have the names of all the cities. And the pplot command uses the Delaney triangulation, the same one we're using for the road network. It also uses it to determine what is the best placement of the label such that they intersect with as few other edges as possible. And this is its best guess as to what is the best placement for the names of all the cities. And that's part of Matlab itself. It's not a Matlab capability. And then one of the things we might want to do is, as an example, determine using our Dijkstra procedure what is the shortest path on this road network? And we can pick 2 points. One would be High Point, which is node number 10, and then from there to Goldsboro, which is node number 7. So for that example, we can calculate, we get a total distance of 156 miles, and then this tells us the sequence of cities that we visit along the way. The second output argument is the indices of the cities, so we can use that and apply it to the cell array of city names, and it tells us then what is the sequence of cities that we visit going from High Point to Goldsboro. And then if we want to plot that, I'm going to plot it as a very thick yellow line, and I'm using the line width property. I'm setting it equal to 3. The actual default value I think is less than 1. It's like 0.5. So this will be a thick yellow line, and it's displayed it on top of the network, so the yellow shows up clearly. So this is a way of displaying what is the actual shortest path. Another thing we could do is if we want to determine what is the minimum spanning tree, and the minimum spanning tree in this case, assuming undirected arcs, is what set of edges connect all of the different cities at minimum total distance. And we can display that. In this case, I'm going to display it as a slightly thinner, I'm using a line width of 2 instead of 3, green line. The next example is using the actual US road network. And for that, we're going to be using the US road node information. That's a data source available as part of Matlab. And for that data source, all we want are the longitude latitudes of all the road nodes. And then for the edges or links, we're going to be using the US road link data source. And for that, we want both the arc list and then as a fourth input argument. So in terms of calling subgraph, the first call is the longitude latitude of the nodes, and then we have a empty array as a second argument. That would be a logical vector to give us a subset of the nodes. So by doing this empty, we're essentially saying all of the road nodes are possible. And then likewise for the edges, we're going to extract all of the road edges for the entire United States, but then we're going to restrict it such that the restriction, which is the fourth argument, is restricted to having edges that have type just equal to I for interstate. So the way subgraph work is you specify node and arcs, and then for each of those, the following input argument would be a logical vector that specifies what subset. So for road node, we don't specify anything. For the edges or links, we're specifying just give us the nodes that have the type interstate. So when we do that, we can call this subgraph routine. And unfortunately, one of the methods that is in the graph and digraph methods in Matlab is also called subgraph. So we're using the same name. This subgraph is the subgraph procedure that is part of Matlab, and it's okay as long as we haven't specified a graph object that we're trying to not apply subgraph. In this case, I think Matlab is smart enough to know that when we call subgraph, in our case, when we have input arguments that are not graph objects, it knows that we're referring to another version of subgraph. So even if it tried to solve using Matlab subgraph procedure, since it didn't match the input argument, since this is not a graph object, it then continues the search, and then it finds subgraph within the matlog folder, and then it executes that. So currently this should not cause a problem in terms of conflict, even though the same name is being used. So I've created this, and first I'm going to pop up a map showing the entire United States, and then I can plot in red all of the, so these are all the interstates in the United States. And it would be a much denser network if I included all of the non-interstate roads. So this is just a fairly small subset of the total number of available nodes. In terms of the actual numbers, if I look at the XY, it has a total of about 10,000. And if we had the whole data set, it's over 70,000. So it's about 1/7 of the total. And then I can title this. And you can see here, it says U.S. Interstate Road Network. So this is a nice representation. One of the things, though, when you look at it, is that it includes a lot of additional nodes that give the shape information. And, this corresponds to what the actual interstates, how they're actually routed. But for most logistics applications, functionally, it doesn't really matter exactly where you travel going, say, from this point to this point. Functionally, it would be okay just to know what is the total distance along this path. And then in terms of the graph itself, you could just basically have one arc that would connect both of these points. So this is an example of an application where it makes sense to consider thinning the road network, so you eliminate all of those degree 2 nodes that just have shape information. They're not really adding any connectivity information to the underlying graph network. So before doing that, first I'm going to call the Dijkstra procedure. So here I'm not using the demo procedure that I used earlier for the small network. Since this is a large network, I want to use the Dijk procedure. And then I'm going to take my arc list and convert it to an adjacency matrix, which is the required input arguments to Dijkstra. And then the second input argument is saying I want to start from node number 1. And then since I'm not specifying a third input argument, it's then going to go from 1 to all of the other nodes. If I had a particular node that I wanted to reach as my destination, then I could specify a third input argument, which would be the node index for that. And then the Dijkstra procedure would stop as soon as that node is reached. But in this case, it's going to go from node number 1, wherever that's located, to all of the other nodes. And I'm doing tick-tock to record the time required. So it's solving this. And it's completed it. It took just over a minute, 64.56 seconds to solve. If we look at what is the total number of arcs or edges, it's a little over 11,000. And that's just the nodes that are part of the interstate road network. We can use the Matlab function called thin. And what thin does is if we take the thin value, it gives us a reduced arc list representation. So if we look at TIJD, it has only 1,200. So it's only about 1/10. So about 90% of the nodes were just degree 2 nodes that were used for shape information, and only about 10% of the nodes were the ones that actually had shape information that had 3 or more arcs incident to them. And those are the really important ones. So what I can do then is use the subgraph again to take the original set of all the nodes, and then I'm going to take all of the nodes. So I'm not, the second argument, I'm not doing any changes to the nodes. I'm going to then take only the arcs that are returned as the thinned arcs. In terms of the indices of the XY, the thinned representation still has the it basically includes indices up to 11,000, which are the total number of nodes. So to be able to reduce the indices to match a much smaller subset, we can call the subgraph routine. And essentially what it does is it relabels the I's and J's in the thin matrix so that they correspond to the reduced set of nodes that are only needed in the thin representation. So XY, before we call subgraph, has almost 11,000 nodes. And then after we call subgraph, now if we look at XY, it's down to 860. So it's reduced the set of nodes, and then also it's redefined the IJD to be the same as the thinned. The difference is that the IJDs here have indices going from 1 to 862, whereas originally, before we did the subgraph routine, the thinned IJD has indices going from 1 up to over 10,000. So it's done essentially a relabeling. And that's the reason to use the subgraph routine, because if you try to keep track of doing that manually, it gets very confusing. So it's nice to just let subgraph do all of the work of doing the relabeling of all the indices in the arc list after you've taken a subgraph of the total. And then the last thing we can do is plot in black the underlying thin network. Let me expand this so you can see. So this previously winding arc now is just a single straight line, and it's a much greater reduction in total graph size. So if we go back to solving the shortest path problem, I'm going to re-execute that same command. Now IJD is the much smaller graph. I get less than 1 second versus 64 seconds, so that's a big reduction. And the IJD itself now is only 1200 versus the much larger size before. The last example, and it starts here in the script, number 4, shortest road travel time, and goes all the way to the end here. Most of this is something that in Matlab's context, you could almost take all of these cells and really make it into almost like a function. This is something that you'll be reusing for a lot of applications. The reason I didn't make this a function is that first, I think it's important to understand what are all the different steps. Secondly, that every time you use it, you might have to make slight modifications. But having said that, this is pretty much a somewhat fixed template for creating a road travel time network. So I'll go through the different examples, but this is something that you'll be utilizing when we get to routing, and you then need to determine what are the travel times and distances between a set of nodes. You can basically use these set of cells in this script to generate your travel times and your distances between all of the entities that you're interested in. And this is sort of the underlying step. So you might want to take everything that's in here and put it into a function that you keep for yourself if you want to keep reusing it. This is something that is, going to be a set of code from a script that we'll be reusing on a regular basis. Again, it talks about a particular example for Raleigh. So if you're doing it as a function, you of course want to generalize it. So you could specify any set of points. So for this example, I'm going to take the same data of Raleigh with the cities of 30,000 that are within 100 miles, just to give a concrete example of the use of this set of functions. And then what I'm going to do next is, before I apply my subgraph, so I basically now have the set of cities, so my XY, I'm going to label it as XY1, and the 1 indicates that these are the set of city locations, and ultimately this is what I'm really interested in. And then I'm going to be creating another set of long lats that are the nodes of the road network, and I'm going to use that to get the shortest path and times. But then once I'm done, ultimately I'm really just interested in what are the travel distances and times between the different cities. And then I also might want to know what is the path I need to follow if I want to actually execute travel along that path. So to get the US road network, we're going to define an expansion around XY coefficient of 10%. That value is going to be applied to a function that's part of Matlab called bounding rectangle, and it takes the values XY1 corresponding to the cities and puts a rectangle that has about 10% additional space around it. That's just so that we include roads that maybe go outside of the strict rectangular boundary of the points themselves. And then to that, we apply it to another function called isInRectangle. And then from that, we get a logical array return that gives us the values of nodes that are falling within that rectangle. And we apply that then to all of the US road nodes. And then all of the US node rows in terms of the subgraph routine, we apply that together with the arcs. And then what we get returned are XY2, which are the nodes of the road network corresponding to the nodes that are within the rectangle. We get the corresponding arcs. But for these arcs, the values of these arcs refer to just the nodes that are within that rectangle. So the references are to the nodes within this point here, and it's not clear what the underlying values are. So to be able to extract the underlying type information for the arcs, we need to tie it back to the original US road link information. And we can do that by returning a logical vector telling us whether or not that arc that we extracted, where it appeared in the original network. So we use this isIJD value to be able to extract type information from the US road link information. So altogether we get a total of 4 output values. So I can execute this. In terms of the total number of nodes, if we look at XY2, there's a total of about 1,400 nodes, and that's all, not just interstates. That's all of the road networks within just the region bounding all of the cities. And then to get the type information, we can call US road link again. And now this is the case where we use the is_IJD to extract just the arcs that correspond to the edges that are within our rectangle bounding our cities. And then we can use this S. If we look at what S is, this is the information for each arc. So these are all the different properties that are available for this arc. So this is everything in that Oak Ridge transportation data set for roads. So we have now available all these possibilities. What we're going to be using are just two different properties. One is the type information. So first we're going to extract, is it an interstate? And then for the interstate values, we want to make a distinction between rural and urban interstates. So we can do that by taking the is interstate, and then this is the bitwise AND operator. And then urban is just the absence of a rural indicator. So if it's not indicated as being rural, then we assume it's urban. So we're looking for the AND of both of that, and we'll assign that. So if it's urban, it would have a value here, so the absence means that it's rural. And then if it's not a rural interstate and it's an interstate, then we can specify that as being an urban interstate. And then a rural non-interstate road, we can logically say if it's urban and its urban flag is empty, so that indicates it's rural and it's not an interstate. So we have a total of 4 different labels. And then using those labels, we can display the different types of roads. So first I'm going to use the makemap command. And here another option for using makemap, in addition to specifying the points, is we can specify an expansion. So this is the 3% expansion. And then I'm going to keep track of the handles to keep track of the legend for each. And this is the call for pplot, and these are all the rural roads. So there's gaps here, and those are the ones that are in urban areas. The second call are the urban roads, and those are indicated in black. And then the interstates are in cyan, which is a sort of a bluish, light bluish color. So now that we have our road network, we need to connect our cities to the road network, and we can do that by calling the add connector procedure. And its input arguments are the set of city locations, the node locations, and then the set of arcs. So with all of that, it creates a total of 3 output arguments. And the way interpreting the output arguments are first that the IJD11 corresponds to any arcs that connect a city to a city without going through the road network. The IJD12 are from the cities to a node of the road network. And then the IJD22 are the edges that connect nodes of the road network to another node of the road network. So that's the interpretation of the 1s and 2s. So we have 3 different types of arcs. We can then plot the points and then label the cities in green. Next step is we can convert the road distances to travel time, because we don't want necessarily always just the shortest path in terms of distance. Most often we actually want the shortest travel time path. So we can take distances, convert those to travel time by making estimates of what the average speed of travel is along each segment. So in this case, I've listed, these are just estimates of, likely to be reasonable values. And you could adjust these. So if you were making this a function, you'd want to make this a parameter that could be changed depending on how optimistic you are or pessimistic about actual travel times. So notice that for interstates that are in rural areas, I'm assuming it's 75. So even if the posted value is 70, you're going 5 miles above the speed limit. And then for urban areas, 25 miles an hour, assuming the posted speed is probably on non-residential streets, it's probably 35 to 40, maybe 45 miles an hour. But the 25 is to account for stoppage at red lights. Alternatively, you could actually explicitly include any node that you go through. There's a certain delay as an expected delay time because of red lights at nodes. That would be another alternative. In that case, then the node traveled speed could be 45 miles an hour. But in this case, I'm just going to take an average of reasonable amount of stoppage time and assume that on average, including stopping time at red lights, you can travel about 25 miles an hour. So I'm going to then assign all of these to a structure V. And then I can take those as the denominator relative to the distance and define a new arc list where instead of distance, I'm going to specify the travel time. And I'm going to do that by specifying the third column in the IJT matrix. So first I copy over all of the IJD values to the IJT, and then I replace the third column with the calculated or estimated travel times. And then for my road-to-road travel times, I'm just going to copy the distances directly. And then for my city to node, so these are ones that are from the facility, or here it's labeled generically as a facility. In our context, it's actually cities. When in most applications, this might be a distribution center or a manufacturing facility or a customer location. So in general, I'm going to copy over the distances from which were retrieved from the add connector function up here. And then I have to come up with what is an expected connector travel time. And I've assumed my average here is about 20 miles per hour. So I get my facility to facility arcs, and I'm going to essentially assume that they're ignored. So the IJG11, I'm assuming there's no roads that connect cities without going through the road network. And again, I think for most applications, you probably don't need to consider the 1-1 nodes. You can assume that you're going to be using the road network when you go from one facility to another facility, as long as you have a reasonably dense road network. I think if I was using the interstate road network, there might be areas of the country where there are no interstates. So in that case, the 1-1 node arcs added by add connector would be relevant. But when you're using the entire road set within a region, it's probably not necessary to include the 1-1s. So in this case, I'm not doing that. And then I'm going to take the IJT, which is travel times, and then apply them to the Dijkstra procedure. And I'm going to do it by creating my adjacency matrix by concatenating two different arc lists. One is the ones from the cities to the road network, the 1-2s, and then I'm going to add to those the 2-2 values. And then the only ones I actually am interested in are the distances from city to city. So when I call the Dijkstra procedure, I'm going to take n, which is the number of cities, and then specify all of the distances only from 1 to n and 1 to n. So in this context, if we look at what n is equal to, if we look over here, we only have 16 different cities. So we're looking at a 16 by 16 matrix that we're interested in calculating. So we're going to calculate the shortest travel time, and then the second output argument of Dijkstra is a matrix of predecessors. And it did it in just 0.3 seconds. If we look at the size of what t is just a 16 by 16. So we're basically using the entire road network just to get the shortest travel times. And then essentially we're sort of throwing away all of the road information and just keeping that 16 by 16 travel time. And then we also have the P matrix, which is a predecessor matrix, which in terms of size is a 16 by 1417. The reason it's so much larger is that 1417 corresponds to the number of total nodes that we have available in our network. So it's a much larger number. And from that, we can extract the shortest path. The distance to the shortest path time, when we look at the shortest travel time route, that's not necessarily the same route that you would get if you were looking at the shortest distance route. So if we want to know what the distance of the different routes are, we can't use Dijkstra directly on the distance information. Instead, we have to take the path determined for shortest travel time, which is encoded in our P matrix of predecessor values, and use that to then calculate what is the corresponding distance of that shortest travel time route. So I'm going to create an adjacency matrix using the city to road and then road to road arcs. Call that W. And then I'm going to start off with a 16 by 16 matrix of distances and initialize them to all have a value of 0. And then I'm just going to go inside of 2 for loops. And then inside of each for loop, what I'm going to do is use the function pred to path. This is my predecessor value that I pass as a first input argument, and then I do that for each combination of i's and j's. And then the W information is the second argument required for a function called location total cost. And what it does is it takes a sequence of values and then applies them to elements in the W matrix. Essentially what loctc does, it does the same thing as earlier in the script when we did the diagonal, applying it to the distance matrix. So essentially what we were doing here to extract the ij values by taking the elements in a matrix and then taking the elements along a diagonal. Everything that's happening in this step here is embedded, since this is such a common thing, we embedded in a function called location total cost. And then given a vector of sequences along a path, it'll then extract the corresponding elements from a matrix W, which in this case then will be the adjacency information. So we can do all of that in this for loop. And we end up now with a matrix D that has all of our distance information corresponding to the shortest travel time routes. And then as a last step, we can take this information and apply it to the same 2 cities that we talked about earlier for the Delaney triangulation. In this case, High Point and Goldsboro. They're, again, nodes 10 and 7. And notice in terms of the arc list, by concatenating them in this case, all of the low number nodes between 1 and 16 are at the beginning of the arc list. So when we can put all these together, all of the road nodes are ones that have values greater than 16 in terms of their underlying node network. So we're taking advantage of the fact that all of the cities are at the very beginning of our arc list. So we can do that, and then we can call the Dijkstra procedure, get the total distance, and then if we want to plot that, we get the yellow line, and this corresponds then to actual road distance. Previously when we did the Delaney triangulation, we just had city to city, but this is giving us our actual road distances. And then we can put a title, and here I'm going to include both the distance and what our estimated time would be for all of this. And then when we bring it to the foreground, you can see here I've labeled all the different elements, and here we have High Point, and then here shows the yellow road estimate of where you would travel. Notice that when you go in Raleigh, instead of going through downtown Raleigh, which would be on the shortest distance path, you're going around the Beltline, and then you continue along I-40 until you reach, I think, US 70, and then over to Goldsboro. So this is the total path. In terms of distances, we're estimating that the travel distance is 143.5 miles, and then the travel time is 2 hours and 28 minutes. To compare that to Google Maps, I've already put in the information for going from High Point to Goldsboro using Google Maps. And in this case, using the shortest travel time, we get an estimate of 2 hours and 33 minutes. So that's within 5 minutes of what we've estimated. And the distance is 144 miles. again, that's almost exactly what we found. So our estimated travel times are probably pretty close to what Google Maps uses when they give you an estimate. And in terms of the velocities and stuff, they weren't designed to actually match this value. So I guess it's just based on what I assume is an average travel time, which must be fairly close to what Google Maps is also using. So it's not always the case you get quite this close of a match. But you can see that, this is sort of the underlying mechanics of what's happening in Google Maps when you solve a problem like this.